Let's do a quick recap of implicit differentiation in section 3.7 in your book. So, what we're going to do is we're going to start with a function that's implicitly defined. Something like x cubed plus y squared minus 2xy equals 2. And I shouldn't really say consider a function. I should say consider y. Because what we're going to see is that this might not necessarily be a function. Now, the points on the graph of this equation are the ones that satisfy it. So, for example, negative 1, 1 is a point on the graph of this equation. And why is that? Okay, because negative 1 cubed plus 1 squared minus 2 times negative 1 times positive 1. Well, I have negative 1 plus 1 plus 2, so that actually equals 2. So it satisfies our given equation. Another example of a point on this graph is the point 0, square root of 2. That is a point on the graph of this equation. If x is 0 and y is 2, square root of 2, then we have a solution to our given equation. Now let's graph our equation and see what the graph looks like. We want to graph x cubed plus y squared minus 2xy equals 2. Okay, there's our graph. So we have a graph. We can see it's not the graph of a function, actually. It doesn't pass the vertical line test. And so we need to we cannot solve for y. Okay, we cannot take this equation and have an explicit function for y, saying exactly what y is. However, you can look at, say, the point negative 1, 1 and consider a tangent line at that point. There is a tangent line at that point. Let's see what that is. So here's our graph. We have the point negative 1, 1, and we also have a tangent line. This line here is our tangent line at the point negative 1, 1. Okay, so this line right here. And it has a slope. We can say something about how the y value at this point changes when the x value changes. So we should have a value for dy dx. How does the y value change as the x value changes? So now we need to be able to actually find what is that value dy dx. And we can do this algebraically instead of trying to estimate it from the graph. Okay, so let's go back to the formula, our equation of that graph. X cubed plus y squared minus 2xy equals 2. And what we would like to find is dy dx. Okay, we know y changes as x changes. So we think of y as a function of x around that point negative 1, 1. So we want to find dy dx at negative 1, 1. So what we're going to do is we're going to take this equation and differentiate both sides with respect to x. Okay? So when we take the derivative with respect to x on both sides, we do need to do it to both sides. Okay? We also need to think about y changing when x changes. So we're going to distribute this derivative function because the derivative of a sum is the sum of the derivatives. And the derivative of 2 with respect to x, that's the derivative of a constant, that's just 0. Okay, now let's take each term. The derivative of x cubed with respect to x is 3x squared. Now we want the derivative of y squared with respect to x. Here we need to think of this as a chain rule. Okay, first we're going to take the derivative with respect to y, we get 2y, and then multiply by the derivative of y with respect to x. We don't know what it is, that's what we're trying to find, but we're going to multiply by the derivative of y with respect to x. And now we have the derivative of negative 2xy with respect to x. Here we have a product, and so we need to use the product rule. So we're going to add, we're taking the derivative with respect to x, so we need to take the derivative of negative 2x first. So we get negative 2 times y plus, now we're going to leave negative 2x alone, and we need to take the derivative of y with respect to x. So we get dy dx, and that equals 0. Okay, and now at this point we want to figure out what dy dx is. We want a formula for dy dx. So right now you can either solve for dy dx. We've got a dy dx here and a dy dx here. So we can try to move everything to the other side that doesn't have a dy dx in it, and then try to get dy dx by itself. Or we know we're trying to find dy dx at a particular point, and it's at the point negative 1, 1. And so we can go ahead and input negative 1 for x and positive 1 for y. And so let's do that right now. So we get 3 times negative 1 squared plus 2 times 1 dy over dx plus negative 2 times 1 plus negative 2 times negative 1 dy dx equals 0. So we've got some simplification that we need to do. On the next slide, I'm just going to go ahead and do the simplification. Okay, here's the simplification. So let's solve for dy dx. So I'm going to do 3 minus 2 is 1 and move it over to that right side. So I get negative 1 equals 4 dy dx. And so dy dx equals negative 1/4. Okay, what does that say? It says at the point negative 1, 1, the rate of the instantaneous rate of change is negative 1/4, or the slope of the tangent line is negative 1/4. If we go back and look at our graph, that's saying this line has a slope of negative 1/4, and that looks very plausible. In fact, over on the left-hand side here, it actually says exactly what the equation for that line is. It's x plus 4y equals 3. If we were going to go ahead and solve for y, we should get negative 1/4 x plus 3/4, and we see that slope is right there. Okay, so I'll do a couple more videos of examples of implicit differentiation. Remember, an implicit function is one where y cannot be explicitly solved for. And so we're going to end up, to differentiate, we're going to have to use a chain rule in order to solve for dy dx.